Hello. So I'll be presenting to you a knowledge-guided large visual model for autism screening in source control setting. So my name is Kamada Alex, in the team of three. So in my discussion, I'll be talking about visual data. This is the information which the system will be using. So our visual data is the videos. So you hear me talking about video analysis, like analyzing the video, extracting what information we need. You shall be hearing me talking about large vision models, the models which are used to process work on these videos. You shall be hearing me talking about knowledge-guided AI, like, and this is where AI it doesn't just act on itself, but is guided by the humans, then supervises classification, where we classify behavior, but under our supervision, then resource constrained healthcare, where resources are not enough, but we need to achieve something in the health sector. So we have a lot of related works on this topic, but as you can see, most of them, they had either high computational costs or they were focusing on only one model, or some of them were not optimized for some features. So ours come to address this. So what are domain application problem? We can see that autism spectrum disorder relies on expert observation, which is time consuming and subjective. And then in our country, you can see that many of the clinics we have here, they don't have access to trained specialists and the reliable screening tools. And even the methods that are existing are manual, for example, just questionnaires. So there is need for an automated, affordable, explainable AI system that assists these clinicians in autism detection. So our computational problem, we can see that autism screening through video analysis involves complex multimodal data, combining motion, appearance, and the contextual cues. So the systems which are existing are computationally heavy, one model, and they most of the time is lack of explainability. So the computational problem we are addressing here is design a lightweight, interpretable AI model that uses multiple data sources. So our model must be accurate in classifying that this behavior is autistic or not. So what are research questions and objectives? So objectives, first of all, was to integrate technical knowledge into AI models, then to analyze the performance of these models as they learn, then to design a framework which is AI based and we don't we shall be using for screening for autism. Then our model must be affordable and scalable. So what questions we ask ourselves as we achieve this? We can see that what patterns can we classify as autistic? Then what features contribute most to autism? What models can we build to capture those features? And what strategies are we going to use when building those models? So far our contributions, we have developed the knowledge-guided AI framework. We have created a structured behavioral compass. This is a data set complement on the existing ones. Then we have developed a novel feature fusion model, and we have built the first integrated autism screening tools using large vision models. So this is the methodology and the architecture of our system. This is our system will be working. First of all, we get a video, like a raw video. And after getting the video, we move the next part, which is extracting those features from the video. After I extract the features from the video, they are fed into our model. So when they are fed into our model, there are three models. And I'll be talking about all of them. There is a TSN model, there is an SGCN, and STGCN. So after our models, what we get, the result we get from those models are fused into one model. So this oral model inference pipeline runs on our deployment. So the users, they just access it via web interface or these API endpoints. So after we get the results, again, our system does what we call the knowledge guidance. Like we don't just output results from an AI, we have to guide it. Then after we get a report. So that's how our system is working. So when I explain one model, I'll start with STGCN. So STGCN is spatial temporal graph convolutional network. So spatial meaning we are capturing the space part of it, then temporal time part of it. So graph, you can see that the human body can be represented more than just being an image. You can map it out into a graph where we have the joints acting as the nodes. So this STGN models that does the spatial temporal graph is a spatial temporal graph convolutional network. The first part is spatial graph convolution, where we first work on the spatial part of it. That is the relationship between every joint. How is this joint related to this joint? And we keep adding the weights. So as we can see from this equation, that is the learnable weights. Then Z is the normalization constant to balance at contributions, like how is this joint related to this joint. You can see that a joint in the elbow is more related to the joint in the shoulder compared to how a joint in the elbow is related to the joint in the ankle. So after getting that and the weights, we do the temporal convolution. Temporal convolution, like the time part of it as time progresses. So temporal convolution, we can see that is done on one node or one joint, but between the different frames. So it applies 1D convolution across different frames. Then after we get our output, then our output, we apply source marks on it, or I can say we do regression, it is fed into a regression head. So in our regression head, that's where we apply our labels, and our model learns that this behavior is autistic or it's not autistic. So after that, the result is fed into our fusion model. Then the SCGN model, it works in the same way as the STGCN model, but the only difference that the other one does 3D pose estimation, and this one works on 2D. 2D meaning two-dimensional, then 3D is three-dimensional part of it, meaning there's the X, Y, and Z, but this one has only the X, Y. So this one does only it removes the temporal part of it. That's only the spatial part of it. So as you can see from this mathematical foundation, you can see that we do what we call the graph convolution, whereby we shall capture every joint and we see how these joints being related. So we have the node feature matrix, then the adjacency matrix. Adjacency matrix, how these joints of the body map is mapped by that the shoulder is here, the joint of another shoulder is here, then the joint of the elbow is here. So when you map up the whole thing, that's what we call the allegiance matrix. Then the weight matrix is how much this one contributes to the other. So after that, we do the attention weight computation. That is computing how the whole thing is related, the other joint is related to the other joint. Then after, uh, we do what we call the semantic feature fusion, where we now get the overall and then we feed it into our regression head. Then in the regression head, that's where we can classify the behavior as being autistic or not using the ADOS score. So the ADOS score is used to train it. Now, after it has learned, now it can predict it based on what it has been fed in it. And the next model, the TSM model. So TSM is temporal segment network. So temporal segment network here, we divide the whole video into segments. Then for each segment, we get the frames from the segment. So after getting the frames from each segment, we divide them and then we feed them into a deep CNN. So the deep CNN performs the computation of it and get the features. So after getting the features, we aggregate them, like aggregating them, like getting an average or a mean. Then after aggregating it, then we apply softmax on it, or we feed them into our regression head, and then we can classify or give a label to it. So we use this a score which goes from 1 to 10. We wanted a very wide regression range. So we use the MMASD dataset, that is multimodal autism screening dataset, which was a very good resource got online. So this dataset included the optical flow, 2D secretons, 3D secretons, and even a CSV of adult ratings. So here is a graph of the activities which were in that data set. There were 11 activities, and this is how they were distributed. You can see from the graph and the pie chart. Then after we made our own data set, because we need knowledge guidance, so we had to make a knowledge corpus. So the knowledge corpus was a text-based data set in a CSV format, which was later used to guide our model. So after we trained our model, these are the outputs. These are graphs comparing the predicted square compared to the true score. We can see that our models were performing very good. This is how the TSN, SGCN, and the STGCN models performed. So here we can see the mean square errors, root mean square errors, mean absolute errors of all the models, the STGCN, the CC, the TSN, the SGCN. So here is the classification report that here it was according to all the classes. When you train a model to classify, this is how the precision was for each class, for equal F1 score, and the support. So more on the models. So this was after we fused the models. You can see here is a graph for model performance. You can see that TSN performed better in fusion. Then here is a graph of the best single mode and the compared to the fusion mode. You can see that fusion actually was helpful. So as I move on, you can see that immediately model selection. So we made 3 models. Instead of selecting one, we decided to choose all because we wanted to capture all the features, the 3D part, the temporal part, the 3D, the 2D, and the optical flow part of it. So now deployment pipeline, you just upload the video, do the processing on the video, you output a report. And this is how you can see it. Like you upload via web interface, we do the processing via vision models, and you output is a report. So the demonstration of our product, I'll do a video on that. So these are the limitations we faced, like the models were complex, so they required the high computational power. But since our aim was knowledge constraint settings, we ensured that users just upload a video, they don't have to worry about it. But in future, we hope to use lightweight architectures. The SGCN model had missed to capture the temporal part of it, but still the 3D models will be handling that part. Then our testing was done on a controlled data set, so we need a more testing which is clinical and internationally recognized and approved. So in conclusion, our model worked successfully, as I'll be showing you in our demonstration. Our models are effective. We demonstrated them. So in the future, we hope to expand our data set to cover a lot of things like speech, how people are speaking, different groups, different environment. Then if using all those models, then we shall have tools which can screen in real time, like not having to wait for anything to be uploaded and getting results, and even getting clinically validated. So here are some of the references. In conclusion, I would like to thank our supervisor, Dr. Galwang Marvin, the creators of the dataset we used, okay, University for the sources like Wi-Fi, library, the cargo and open source communities, the deployment platform. Thank you.